And I am going to talk about that. So this is of GK modules, but what it's for, I mean, before doing it, I want to say that what it's for is making some relationship between group representation, reductive group representation, and Weil group representations stuff. That's what it's for. And the reason that I say this is that this is a huge idea. And this is I want to mention several other incarnations of this idea that are not about coherent continuation. Well, let me just say something. So suppose I look at GLN over a finite field. So this is a finite group, and it, the order it is q to the n minus 1 times q to the n minus q times q to the n minus q to the n minus 1, and you can rewrite this in a bunch of ways. Actually, an interesting way is to write it as the sum over sigma in the Weil group of let's see, q to the power the length of sigma, and then what have I left out? I guess it's q minus 1 to the n times q to the n times n minus 1 over 2. So something, I'm not even sure now what the degree is, right? But it could be. Anyway, this, well, this is the symmetric group here. I mean, some formula like this is true for any split reductive group, but the point is that sort of what this so this is the order of this finite group, and the point of this formula is that this is supposed to be sort of a Q analog of the symmetric group. So never mind this unfortunate Q minus 1, except for this nasty Q minus 1, this suggests that the order of GLN over a field with one element should be, well, this sum would just be the symmetric group, and, well, never mind the 0 to the n, but we'll just ignore that, and then, well, at any rate, this kind of business says that you want to relate the representations of GLNFQ to the representations of SN. So as I say, that's what the coherent continuation is going to be about for real reductive groups. But I want to just remind you of how this can be done. So if I take B is upper triangular group over F cubed, then the Brugha decomposition. Oh, sure, why not? That sounds pretty loud.
Yeah.
Okay, the Brugha decomposition says that G is the disjoint union over, W of these double cosets, like this, and these come in as permutation matrices. And, well, there's an interesting representation, which is the functions on G mod B, and the dimension is the cardinality of G mod B, which is this number that I wrote up here. It's the sum over the symmetric group of Q to the power of the length. And the question is, how reducible is this? How do you break this representation into irreducible pieces? And the answer, which is entirely elementary, is that if you look at the G homomorphisms, I should give this, just these functions on G mod B to itself. The G homomorphisms here, the dimension of this hom is the sum of the squares of the multiplicities of irreducibles. In this representation. But at any rate, what this hom is, it's naturally identified with B bi-invariant functions on G. In other words,
the C of G mod B, that's the vector space of functions of
this is all functions on G mod B, and if you take bi-invariant functions, then this acts on the functions by convolution on the right. And convolution on the right won't interfere with the G action. It'll commute with the G action on the left, and that's how this gets to be an isomorphism, and well, so the theorem is that this hom over G of this functions on G mod B to functions on G mod B is isomorphic to the convolution algebra of B bi-invariant functions on G, excuse me, and the dimension of this thing is the order of the Weil group because of the Brouillard decomposition. There's a basis consisting of the class functions on these double cosets. And what this convolution algebra is called the Hecke algebra. Well, and what happens is that it's generated by these elements T sub S. This is the class function of well, the SB for S a simple reflection. In other words, this is the transposition of adjacent things, like that. It has these generators, and well, it has a basis. These TWs. This is the class function of BWB, and it, well, so in particular, there's the identity element. It is this T1. I forget what constant I should put in the convolution, but at any rate, these generators, the relations they satisfy are the braid relations, the T S T. Where this is, well, this has the number of terms here is 2 or 3, depending on whether or not S and T are next to each other, just as in the Weil group. And then there's a quadratic relation which says that TS plus 1, well, I'll write it like this. TS squared is Q minus 1 TS plus Q, thing Q. Which, well, this is a computation in SL2, basically. Okay, so these relations, this is a Q deformation of the defining of Coxeter's defining relations for W, which are you know STS is equal to T at ST like that, and S squared is equal to 1. So these relations, well, the braid relation is exactly the same, and then the quadratic relation does this, the 1 is replaced by a Q, and you get this extra Q minus 1. At any rate, what I guess it was Titz who showed that the irreducible, well, this Hecke algebra is, well, it is semi-simple for all positive values of Q, and therefore isomorphic to the, well, sort of the value at Q equals 1, which is the group algebra of W. So at Q equals 1, as I say, you're just getting the group algebra of W. Okay, so what do we got? So what we know is that this self-intertwining algebra of these functions on G mod B is isomorphic to the group algebra of W. And so what we conclude is that these functions on G mod B decompose as a sum of the order of W hat distinct irreducible representations, I don't know, pi tau, with the multiplicity of pi tau is equal to the dimension of this W representation, tau. So I'm telling you old stuff, but the point is, here's some interesting information about representations of this finite Chevalley group expressed in terms of representations of the Weyl group. And that's the kind of thing that people try to do with representation theory, over local fields in general. So
I have a historical question.
Yes.
So do you think that was motivation for Greg Zuckerman when he thought about this stuff?
No.
Okay, just one.
Yes.
If I remember research correctly, these are all Q that are not a root of Q.
I think that's correct.
It's not really relevant.
I think, and you have to rule out 0. I think I think you're correct. Yeah. At any rate, the order of a finite field is never a root of unity, so we're good. So, okay. So this is the kind of target theorem. And well, so let me just stop with the idle philosophy and get to coherent continuation. So we've got our G and K. Yes.
Just get confused by your last box sentence.
The this is a GLN FQ representation. And the multiplicity of this representation in the functions on G mod B is given by this dimension.
one.
Well, so the number of distinct, I don't know how to say it. So in general, if you have some representation which decomposes as a sum from I equals 1 to m of ai pi I, where these guys are distinct irreducibles, then hom over g of pi into pi becomes the sum from I equals 1 to m of an AI by AI matrix algebra. And that's what I mean. So we've identified hom over g of this into itself. It's the group algebra of W, which is the sum of matrix algebras indexed by the irreducible representations of W and of sizes the dimensions of those representations. And therefore, I'm saying, yeah, I don't know how to say this better. I'm saying that if I list all of the distinct representations that show up in this decomposition, they can be indexed by irreducible representations of W, and the one that's indexed by a particular representation, that's how often it occurs. There's probably a better way to say that, but
I think in this case, you have two commuting algebras that are the centralizers of each other. So you get pi tensor
yes.
pi tau, and then the dimension.
Okay, I think
Okay. So, yeah, so this, here the idea was you compute some commuting algebra, and then by doing generators and relations stuff, you somehow relate that commuting algebra to the Weil group, and, well, end up with a theorem like this. So how do we get Weil group? Again, we have this M of GK, this, maybe I'm going to write F of GK. This is the category of finite length. GK modules. And what I want to do is what happened over there. More or less, I want to attach interesting W representations to well, irreducibles in here. And I mean, these are the ones that Jeff was talking about in the first lecture. I want to explain what they are. Okay, so so the idea comes from Janssen, who used it to study this BGG category O. And it was Zuckerman who applied it to GK modules. And so what the idea, the basic serious fact is that if F is a finite dimensional representation of G, and, you know, of course, always algebraic, and well, either M is a module in category O, or M is one of these finite length GK modules. Either of these cases, then if you form this tensor product, it's either in category O or in F of GK. So
You don't need algebraic for that.
you need the K action to be algebraic in order for the GK. Well, I mean, here you need the action to be differentiable. I mean, you need a finite dimensional representation of the Lie algebra, and no, it doesn't have to come from an algebraic group representation, but here you need algebraic on K, but
That's not automatic for finite.
no.
Okay, no.
Actually, anyway, I want to work with finite dimensional representations of G, and so what happens is that so that each M is now part of a family. Well, these various F tensor M's as F can be any finite dimensional, and well, the sort of number of these things are parameterized by dominant weights in X upper star. And well, the question is, how does this family vary? Well, there's still more modules. If you have any gamma H star, this is our fixed cartan, H, this corresponds to an infinitesimal character. Which is the same thing as some maximal ideal, I don't know, I gamma in the center of the enveloping algebra. And if you have any M in, I'm going to stop talking about category O. The same words apply to category O. Then you can define P gamma of M. This is the set of M in M such that I gamma to the n M is 0 for some n. So this, well, this is obviously a GK submodule. And what's easy is that M is the direct sum over gamma and H star mod W of P gamma of M. So here are two ideas for making new modules from old ones. So now we have I can take P gamma of M tensor F for any F and any gamma. And of course I can repeat. And well, let me do an example. If I take G as SL2 and M is the three-dimensional irreducible representation, and now I take F, it is the n-dimensional irreducible representation. This has weights n minus 1, n minus 3, down to minus n minus 1. And this has weights 1, 2, 0, and minus 2. Then this M tensor F is a sum of representations. This is the sum of the irreducibles of dimensions n plus 1, n minus 1, all the way down to, it stops almost immediately. N plus 1 and n minus 1. It's these three pieces as long as n is greater than or equal to 3. I won't